Alright, we're going to see if this goes a little bit better today than the last video. I have a pause button in the lower left hand corner, so that automatically makes me feel a lot better about this. Alright, what else do we got? Sharing your screen. Okay, that's good. I like that it's sharing my screen. A lot different from the videos I used to make on the smartboard. I'm hoping to, if I do mess up anywhere, I can go back and edit these. That's kind of a game changer for me. But today we're going to look at all the mathematical models that we did last year in pre-calculus A. And we're going to look at some that were in pre-calculus B as well. I did a little bit of looking ahead. There's some that we're just going to briefly go over. Some we're going to go over in detail. If we briefly go over it, it probably means that we're going to come back and see it at a later time this year. Okay? So what is a mathematical model? Well, it's a description of a real-world phenomenon, and there's all sorts of stuff that it can go into. We're going to talk about population size. We're going to talk about a lot of stuff with physics or economic growth or anything that you can just put an equation or a function to. And the purpose is to find this relationship between the two variables so that we can then predict what's going to happen, or maybe understand why something is happening with a relationship of one variable changes and another one changes by a certain behavior. Okay? And so the most basic one that we're going to look at today is a linear model. Now, linear models are going to scale all the way back to our glorious Algebra 1 days. And this is going to be where we had a line graph. Okay? And so what we looked at with this was we either had y or f of x, it doesn't matter, but it was just simply that mx plus b. Okay? Where m was the slope of my straight line, and b is the y-intercept. Okay? Yeah, just like a straight line. I don't think there's any need to go into more detail than that. Let's look at an example problem that will deal with this. It says as dry air moves upward, it expands and it cools. So if the ground temperature is 20 degrees Celsius, ooh, going all Celsius on this one. I don't even know what that would be Fahrenheit. It's probably about average, I guess. And the temperature at a height of 1 kilometer into the air is going to be 10 degrees Celsius. Express the temperature T as a function of h. Okay? Now careful, what that means is T as a function of h. So normally I had y as a function of x. It's just I don't have x's and y's in here. I'm not just dealing with coordinate points. I'm dealing with heights and temperatures. So when it says t is a function of h, t is going to go where the y is, h is going to go where the x was. Okay? So, assuming a linear model is appropriate, I'm gonna try to always tell you which model to use. If it doesn't say it in the examples, then I think it will in the homework, and I know I will do that on your assessments. Not much room to work on here. I think I'm just gonna go over here on the side, I guess. Let's see. So I need two pieces of information. I need the slope, and I need the y-intercept. Once I get those two things, I'm going to be able to plug it in. So the two things I know is that the temperature is going to be 20 degrees when, let's see, that's the ground temperature. So whenever the height is 0, and the temperature is going to be 10 degrees when the height is 1. So first thing I'm going to do is I'm going to find my slope with this. Remember, my slope is going to be, we normally say y2 minus y1 over x2 minus x1. It's just the difference in my temperatures over the differences in my heights in this case. And just make sure you're going the right direction on this, or the same direction rather. So 20 minus 10 over 1 minus 0. Yeah, my slope's going to be 10. For each kilometer I go in the air, I expect the temperature to go down. And I didn't even go the right way. It's good that you see me make mistakes. I say that doesn't make any sense. Notice how the 20 and 0 go together, so I put them first. My bad on that. that'll change it to a -10. That makes me feel better because now as I increase H by 1, the temperature is dropping 10 degrees is what that tends to mean. So I've got my M. My M is going to be -10. Now I just need to figure out what my B is going to be. Okay. So what I can do is I could actually take either one of these points and plug them in for H and T right here. Or remember what my y-intercept is. It's just going to be my y value when x is 0. So I'm pretty sure that this 20 right here is going to be my y value, or my y-intercept. And sure enough, if I plug 0 in for this H right here, all of this goes away, and I get T is equal to 20. And so this right here answers part A. Draw the graph of the function. Okay. I'm gonna check real quick to see if I have a graph. I do have a graph. Okay. Don't let me forget about part C. I will come back to it. But I'm going to have to scale my graph. I'm just going to count by 5s up the t-axis here, and then my h-axis will be over here. So it goes 5, 10, 15, 20. That should be enough. And you can just throw a little 5 right there. That'll signify to me that you're counting by 5s when you're going up and down. And then let's just count. Let's see, h is 1. So we'll just count by 1s going this way. Okay. And so my y-intercept is going to be 20. Okay. And according to my slope, remember this guy is going to be rise over run. So I'm going to rise -10. So this means I'm going to go down 10, run 1. I land right there. Rise 10, run 1. And so the equation of this line would look similar to this. Now they might have thrown in a relevant domain on this because it doesn't really make sense that, I guess it does kind of make sense that the height is going below the ground right here, and you probably could have a height of -1 if you're digging a really deep hole, but I'm not going to get just real picky about this. Okay. Awesome. Now I'm trying to remember what part C said. I think it asks, what is the temperature at 2.5 kilometers? Temperature at a height of 2.5 kilometers. So if I was to keep going up on this, I would expect my temperature to come down 2.5 kilometers. I expect it to be somewhere right here. And I could definitely get this answer from my graph. We talked about that, I think, on the last video. Or probably what's going to be a little safer is if I just take my equation at the top of the screen that is boxed in, and I can just take 2.5 and plug it in for my H. So 10 times 2.5, I do believe that's -25. It's early in the year, but I think I can get by without the calculator on that one. So -5 degrees Celsius. If I go 2.5 kilometers up, I expect that to be the temperature. Awesome. Now, we saw a different way to represent a function the other day. We said that sometimes we use an empirical model or we use a table. Okay? So if there's no physical law or principle to help us formulate a model, we construct an empirical model, which is based entirely on collected data. We do this a lot in statistics. If you're taking statistics next semester, we're gonna find all these points, and we're gonna find that these points don't all lie exactly on the line. They're going to be off for some reason. And in statistics, we're wondering why those are off. You know, why are there those little differences in there? And so here we have CO2 levels. Didn't have 2 in there. I don't know why it did 2. In different years. And so I want to find what the CO2 level is for 1987, which should be right between those two numbers. And then I'm going to extrapolate. I'm going to find out what the CO2 level was 2010, which this table does not even go to. Now you can definitely use a graphing calculator on this, and I'm going to show that to you later in the video. Okay, but if we're just using a linear model on this one, I think that will suffice. And I'm looking at this. I know a linear model is gonna be good enough because look at how much I'm jumping from each one. Looks like I'm jumping like what, 3 or 4? Or that one was 2. I'm not jumping a whole lot. The how much I'm jumping to get to the next line down is constant. And so what we say is that their first order differences are roughly the same, meaning I can use a polynomial that is of degree 1, which is a linear equation. Like I said, I really expected I would say a linear model would be appropriate. So the next big question comes is, which points do I use? Because I'm going to get I could very well get different values if I use different points or different equations. And so some statisticians are going to say, well, you need to use the first point and the second point because those were the first 2 you found. Some say randomly close your eyes and just pick 2 points of wherever your pencil lands. I was always taught to use the first and the last point. Actually, if we were to graph this, we would want to use the points that are closest to the line. But that's something I'm going to get more into statistics. For what we're going to do in here, the first and the last points will always be good, and that will match up with what I've done on my key. Okay, and it should give you a very similar answer if you use 2 other points. So again, I'm looking for my CO2 level is going to be explained by my time or my year. I'm going to use T for my time. So again, the B for the problem is going to be get my hands on the M and get my hands on the B. So first up, I'm going to want to find my M, my slope. Okay, let's see if I can not mess this up this time. That would be great. Remember, it's going to be y2 minus y1. So I'm going to subtract off this one. I'm going to take this 369.4, and I'm going to subtract off this first y value, 338.7, over 2,000 minus 1980. So whenever I did that, I got 1.535. So I've got my slope now. There's a couple ways we can attack this y-intercept. Notice I don't have the year 0 up here. Okay? And some books will say, well, just use your first year as year 0. Again, another topic in statistics that I'll cover next semester if you are in there. So you can definitely do that. Just let me know that the year is 0. Boom, you can plop in this 338.7 as your y-intercept, where 1980 is the same as t equals 0. That's perfectly fine. I'm going to go ahead and work it with just the numbers. All right, the numbers are going to get a little bit gross on this, but it'll work. So far I have this 1.535. I'm going to plug in right here. I've got a couple ways I can work this. Each year, though, it seems like they tell me this is the best way. And so what I'm going to do is I'm just going to pick a point over here. I'm just going to pick my first point. Probably one of the 2 points that I use might be a little bit better. And I'm going to take the CO2 level, and I'm going to put it in right here. I'm going to take the 1.535 I just found, and then the time on that was 1980. Like I said, if I use 0 there, it's going to be okay. It's just going to spit out this as my CO2 level. You just need to somehow let me know that that happened. Okay. So if I multiply these together and then subtract it off, I'm going to get an awesome negative number. Negative 2,700.6 is what I have in my notes. And that's going to be my B. Good news, I got my M, I got my B. I can rewrite this now as 1.535 T minus 2,706. And that is my model. Okay. To figure out what the CO2 level is going to be for these years, now I just have to plug in 1987 and 2010. Now, if you used this 338.7 as your y-intercept, then you're just going to plug in 7 in for t, and then let's see, that would be 30 years later. 30 in for t to get 2010. So you have a little bit more math to do. But the way that we worked it, we get to just plug in the years, and hopefully we get a CO2 level that makes sense. So we're going to pause the video. We're going to try to pause the video, and then we're going to plug both those in, come back and see if you get what I got for the years, or for the CO2 levels. So go ahead and hit pause.
Teachers, I know.
Hopefully I'm back recording, and hopefully you're back with me, and hopefully you got these two answers at the top of the screen. If you didn't, shoot me an email, make a comment in Google Classroom, and we can definitely look at that later on. All right, let's get off linear equations, or we'll probably spend more time on linear functions than we do anything else in here. We just have a lot to cover in this. And again, this is going to be 2 days worth of video. So once you get tired, hit pause, go grab a snack, come back and join me. So polynomials. Okay, polynomials are going to be those big old long things that we did the P's and Q's on, and we graphed them last year, and we solved them, and we did the fundamental theorem of algebra with them. But a polynomial equation is going to be a polynomial, if and only if, it's going to look like this form. And then you're going to have another coefficient raised to a lesser power, all the way down to just a constant. So it's one of those big, long sentences. Now, there's some, I guess I left myself room to actually put it on there, but didn't see that right there. So n is going to be a non-negative integer. Okay, let's talk about what that means. If n is a non-negative integer, that means you cannot have negatives up here in your exponents. That is a different function. On a polynomial, they have to be nice numbers, 1, 2, 3, 4. Integer meaning that it cannot be a fraction. Okay, and then these numbers out in front, the a sub n minus 1, all the way down, these are called coefficients. Okay, and our rule for that is that they have to be real numbers. Okay, so you won't have anything with i's in there. Yes, fractions can come in. Yes, negatives can come in. They don't happen that often, but they are allowed to. The domain on this every time is going to be all real numbers. And then whatever this winner is right here, whichever guy has the highest degree, whatever number that n is, the highest exponent, we call that the degree of the polynomial, whoever has the highest exponent. Okay? So let's go over this. If I have a polynomial degree 1, that's what's going to be something that looks like mx plus b. This is where I make sure you guys are awake in here. I call that what type of function? Linear. Okay. Now, as you can see, I still have this linear function embedded whenever I add something over to it. But as you can see, my highest exponent in this one is going to be 2. So I call it a polynomial of degree 2. More specifically, we call this a quadratic function. I don't have it on here, but if I had degree 3, it would be a cubic function. Okay, and so all of those are fair game. Once we get to degree 4, oh man, I guess degree 4, we call that a quartic function. And then once we hit degree 5, that's when we just call it a polynomial of degree 5. We don't have any special names for them after 4. But it goes linear, quadratic, and then cubic for the 3rd degree, and quartic for the 4th degree. Oh, I went ahead and spilled the beans on it. I promise you I looked at this before, but we have a cubic function. And then this is going to be the graph of a cubic function. Once you get to a cubic function, there's a lot of wiggling that can go on. Okay, so the higher this number gets in front, the higher degree, the more wiggling that's going to go on. We're not going to get, we did all that wiggling last year. We're going to be able to graph it much better this year, but we have a lot of calculus to learn before we get there. But these are going to be some examples of polynomials of degree 4 and 5. All right, so we're going to work this problem a lot in here. We're going to find better and better ways of dropping a ball off the CN tower as we go through this year. So the CN tower, the observation deck, is 450 meters above the ground, and its height, h above the ground, is the height of the ball is recorded at 1 second intervals as it drops. Okay, so I'm up here on the tower. I'm going to hold the ball. I get ready to drop it. After 1 second, it drops 5 meters. And so the height of the ball is only 445 meters. Then, as you can see, unlike the last empirical model that we saw, this time it's dropping 5, dropping 14, dropping 22, dropping 33. As you can see, these numbers are getting bigger and bigger and bigger. That's going to trigger in you that this is not going to be a linear model. I'm going to have to use something a little bit more sophisticated on it. For how fast I want to get through this today, I don't want to really get into how to tell what type of model it is. If you had me for Algebra 2, we talked about how to find what type of model it is, and we can definitely go over that in class. But I'm going to tell you that this is going to follow a quadratic model. And being able to find what it is going to require us to do some system of equations on it. Well, it's been a while for systems of equations. There's actually an easier way to do this using our friend, the graphing calculator. So, let me get back here at my computer for a second. Exit this. And what I've done is I've went ahead and put in, let me go ahead and go full screen on this. I went ahead and put in all of the points that were on that last model right there. And so, let me talk about how to get here. I'm sorry. So I hit stat right here, and then I hit edit. And then I just had to go through and key everything in. So this stat button right here is going to be your friend. All right, that's going to be one that gets you through all this. Here's where the real cool stuff starts happening. If I hit stat again, and I go over to calc, I can do that linear regression that I did a while ago with the CO2 levels, and it will give me an even better answer because it's using something called least squares regression method. That's not for this class right now. Again, take stats. I'm gonna cover it way more than I need to. But remember, I'm going to tell you whether or not we're going to have a linear regression, quadratic regression, cubic regression, quartic regression, all the way down. There's all sorts of regressions on here. Natural log regressions, power regressions, log regressions, sinusoidal regressions. We don't use very many of them. But like I said, on this one, we're going to want to use a quadratic regression. Okay? So it's going to bring up this menu if you're using one of my calculators. If you're not using one of my calculators, let me know, and I will show you the syntax you have to type in on it. So it's asking where my x values are. Well, I just typed them all in like I had them. So L1 and L2 are my list. We're not doing frequency lists in here. We will next semester. And there's a pretty cool little thing you can store your regression. I'm going to go ahead and store my regression. You do not have to. It's just so cool how it works. I'm going to geek out for just a second. So don't worry about storing it. But the big thing you want to do is calculate it. And what it does is it tells you what the coefficients are that you plug in for A. It tells you the coefficient that you plug in for B. And it tells you the coefficient that you plug in for C. This is called this is all R squared, so that's going to be the coefficient of determination. Don't worry about that. The fact that it's so close to 1 is a very good thing, but again, something outside the scope of this problem. Okay, so that's where to find it. So to answer the question, I'm just going to go ahead. I'm going to go ahead and just write all of this down up on the board in just a minute. Okay, so you'll be able to come back and look at it. But I did store that regression because I wanted to kind of show you what's going on with it. So it says find a model of best fit that will work with the data. All right, so my height right here is going to be negative 4.90 t squared. Just writing this down off my calculator screen. And that is the model that will fit my data. So a great question on this would be, when is the ball going to hit the ground? When's the height going to be 0? Sometime after 9 seconds. And if I'm wondering when the height is going to equal 0, I can just plug in 0 in for the height. And I just simply solved this. If you sat through pre-Cal A last year, you should know how to solve a quadratic. This one's not nice, unfortunately. I can't think of what to guess and check as far as factors of 449.36 to make it so it comes out okay. And so I'm going to either complete the square or do quadratic formula on it. I choose quadratic formula. T equals negative b plus or minus square root b squared minus 4ac all over 2a. And so I'm just going to plug in that a, b, and c right from my calculator. Okay, and I'm going to plug them in for these a, b's, and c's in this equation. And so what it's going to give me, it's going to give me 2 answers, one of which isn't going to make any sense because it's going to be negative. But the other one does make sense, where the ball is going to hit the ground at 9.67 seconds. It's pretty cool how that works. All right, I'll have these graphing calculators in here. I'll also show you a cool app on your phone that you can get where you can definitely do this at home. And so it'll all work the same. This is a good take a break moment. Right? Normally, if this was a normal class, I would be done for the day, and we would pick up the rest of it tomorrow. So take a break if you need to. If not, moving on. Let's talk about power functions. Remember, power functions are going to be little bitty short polynomials is the way I think of it. They're only going to be one term long. And it's going to be x raised to some power. Now there's a lot of rules for that raised to some power. First off, raised to some power can be a positive integer. All right? So it could be, y equals x to the first power. We already talked about that. Y equals x to the first power is just going to be our identity function. It could be raised to the second power. Talk about that as well. That's just my basic parent function of the quadratic. Ooh, big way back here. Remember raised to the third power? Cubic function? Snake on a plane. And here's the good news with it. Once you start going on this, they start repeating after a little bit. X to the fourth, we go back to a parabola. Now, ideally, this is a little bit steeper than the last one. And then down here at the bottom should be a little bit wider. I purposely didn't really draw it with any units on there. And so, and it keeps going. Everything that's going to have an even power is going to take on this idea of a parabola, or this shape of a parabola. Whereas everything that's going to have an odd power, can't really see it on the first one, but it's going to be a snake on a plane. And again, we're talking about the sides right here are going to be steeper, and everything that's between -1 and 1 right here is going to actually be pulled out a little bit more stretched. Okay? And so this was just a really lazy snake on a plane, if you want to think of it that way. But everything that has an odd power is going to follow that snake on a plane. All right, case 2. Case 2 is not as fun. Case 2 is going to be if I raise it to a fraction power, like 1 over n, where n is a positive integer. Okay, and so in math, if we have something raised to a fractional exponent, we can send this n over to be inside the square root right here, and we still have x to the first power, and I just end up with something, a new function called a root function. So for n equals 2, we call that a square root. And on a square root, we go to the points 0, 0, and 1, 1, and we have the beloved swoop. If that's the first time you heard that, you probably haven't had me for math before. And so Everything that's going to have an even, if this number is even right here, it's going to look similar to this. So if I have a fourth root, it's just been stretched a little bit, but you're still going to have the swoop on there. Okay. Right, what about if I have an odd root? What if I have like x raised to the 1/3, which would be n equals 3? Not a big deal. That's just going to be a cube root function. Okay. Now, a cube root function is going to be the lying down snake on a plane. And it's actually going to be the inverse. We're going to talk about that in a few weeks. But that's going to be the lying down snake on the plane. It's got a domain of all real numbers. The range is actually all real numbers as well. There's no isomtopes on this. Okay, the isomtopes we're going to get to in just a minute. Third case of a power function is if I raise the power to a negative number. Okay, for instance, if I take x raised to the -1. Remember, if I take something raised to a negative power and I'm wanting to get rid of it, what I do is I drop it down to the exponent, and I have 1 over x raised to the positive first power. And so this is going to be my basic reciprocal function. Talk about reciprocal functions. This is the most basic one that has horizontal and vertical isomtopes lying on the axes. We don't see this one that often because it's kind of hard to grade, it's kind of hard to stretch. It's doable, but any of them that we encounter in the homework or on assessments, we'll be able to get through them. Now, the reciprocal function is one of the most basic rational functions that we could have. A rational function is simply a ratio of two polynomials, p of x over q of x. Okay. We want to make sure the q of x is not the zero polynomial, so that's usually not a big deal. But the simple equation of a rational function, 1 over x, is just a reciprocal function. Like I said, we just did the basic reciprocal function. It looks something like this. And you're thinking, well, that's kind of cheating. Those don't really look like polynomials. 1, it would just be a polynomial of degree 0, and x would just be a polynomial of degree 1. So if the top and bottom match my polynomial rules, it's definitely can be a rational function. Most of the time, you will see more detailed polynomial over another polynomial. We're not going to go in much detail on that in this section. We will come back and graph them once we get some more calculus underneath our belt. I just want to show you how crazy these things can look. We did graph something very similar to this last year. I think this one it doesn't have a horizontal. I thought it had a horizontal asymptote. But remember, whatever made the bottom equal to 0, this is going to be just a brief overview of it. I am not going to have you graph anything like this. But 2 and -2 made the bottom equal 0. And so we would draw vertical asymptotes there. There's not any horizontal asymptote because the top one. We're going to get a much better way of figuring that out. But I just got a rough sketch of this in my notes. It came out to look something like this. Okay, we can definitely check that in the graphing calculator later if we need to. But these are those crazy looking ones that had the vertical and horizontal asymptotes with the snakes and the branches and the parabolas in them. Next up, algebraic functions. This is sort of new. An algebraic function is just a function that kind of mixes some of the previous ones that we've talked about. And the way that they're going to mix them is using addition, subtraction, multiplication, or division. And so actually a rational function is going to be an algebraic function, but I'm going to want you to call it a rational function because that's a little bit better name for it. But here are some examples. As you can see, on this one we have a quadratic function that's underneath a root function. I'm taking 2 of them. I did a composition of them. I'm taking 2 of them, combining them. That's going to be an algebraic function. On this one, you have, it looks like a rational function, but but it can't be rational because it has this square root in it, and then it has a cube root over here, and they're being multiplied together. Pretty much if it looks like a mess, you've got a pretty good shot at calling it an algebraic function, and you're going to be right. All right, so that's a good takeaway from that slide right there. Here's what some of them look like. Yeah, they're messy. Right? We get to graph some of them though this year. It's going to be good. Well, we spent a long time talking about trigonometry in the second semester and at home last year during the pandemic. So can't let that pass by today. So we always measure in radians in here. Okay? If you see something that has to do with trigonometry, assume that it's in radians. If you have your own calculator and you're using it just for this class, switch it to radians. It won't ever go wrong with you. All right? And so if I'm using degrees, and I can't think of a single homework problem or a test question where I say to skip 2 degrees, but we're going to be using radians. Check our work. All the answers will be in radians. I don't want to see answers written as 60 degrees. I want to see them written as pi over 3. And that's going to be important in some upcoming videos. So let's talk about the sine and the cosine graph. I always like this part whenever you guys are in class because I get to ask you, what does that sine graph looks like? And I love getting the responses. And most of the time, they do remember that the sine function is the one with all these little hills and valleys going left and right. And the hills and valleys oscillate between -1 and +1. They do have trouble remembering the period of sine. By the time I complete 1 hill and 1 valley, I'm at 2 pi units, making it so if I complete 1 hill, I'm at pi. So this would be pi over 2 and 3 pi over 2. What else do we need to know about this? It's always between -1 and +1. That's pretty good. It's known as a periodic function because once I do complete this first period, all that happens next is I repeat another period. It takes on all the same values. It's just everything that you see in these first 2 pi units right here, the period, you're going to see again in the next 2 pi units. Okay. Oh, I forgot to do cosine. Goodness gracious. Let's go back. Oh, look what I did. Oh, goodness. This would be another good editing spot if I remember. I might just hit present. I want you guys to see me make mistakes. I'm on the right slide somehow, though. All right, so cosine. Cosine is going to be the one that starts on the hill right here. Comes down, comes back up. It looks a lot like sine. The biggest difference is that it's got a different starting point. Now, I didn't draw it that well, but it's going to work. It still oscillates. It still keeps all of its y values between -1 and +1. And it still has a period of 2 pi units. So by the time I get back to the top of the next hill, I'm at 2 pi, making the bottom of that valley be pi, and these x-intercepts be pi over 2 and 3 pi over 2. You can definitely find some videos on that if you want to go into more detail with it. I'm just kind of reminding you of these because they will be fair game again after today. I skipped one. Okay, where are we at? Tangent. I like coming up with tangent. Tangent is going to be, remember, it's going to be sine over cosine. So if I was to overlap the two drawings that I just did, remember what I said a while ago about rational functions, was that anywhere the bottom equals 0, that gave me a vertical asymptote. So if you remember cosine a while ago, it came down, it came up, it came back down. So everywhere this thing crosses the x-axis, I'm putting a vertical asymptote there. Get rid of that. And then in between, we actually came up with this last year ourselves. We drew our snakes on the plane. And they just keep repeating forever and ever. I didn't do a good job at spacing those, but it'll get the point across. And so my neighboring isotopes on this are going to be I call it every odd pi over 2. Okay? So that makes it so the period is different. Period, I misspelled period. The period on this is just going to be pi units before it starts repeating itself. The range on this thing touches everything from -infinity to infinity. So we're not strapped between -1 and +1 like we are for sine and cosine. We're able to get any y value on this, especially the closer we get to these vertical isotopes. Guys, we are getting there, I promise. Exponential functions. We're not going to go in great detail about exponential functions. We'll cover exponential functions after the first test. Okay? But the exponential functions are going to be functions of the form a to the x. It always throws me for a loop because I'm like, I already did a to the x. No. I did x to the a. That's my power function. My exponential function, I'm throwing x in the exponent, and I get a to the x. And so I'm going to go ahead and graph these two functions, and I'm going to go into more detail later, but y equals 2 to the x is going to go through here and here. And it's just this little slide that goes up that has a horizontal isotope here. Whereas 1/2 to the x looks like this. Let me label them. So if you get something that's bigger than 1, it's going to follow this red line. Whereas if you get something between 0 and 1, you're going to be following more the green line. So it's confusing me making that red. So it's going to follow the green line right there. And so one's exponential decay, one's exponential growth. Either way, we're looking at the domain being -infinity to infinity. And since I'm not allowed to go below this horizontal isotope right here, it's just sitting on it. Remember, it doesn't touch it, it just sits on it. The range is going to go from 0 to infinity. Section 1.5. We'll do that in a couple weeks. I'm going to go into this in much more detail. Okay? Log functions. Log functions I'm not going to go in very much detail with either. I want you to be able to recognize them right now. It's pretty easy to recognize it because it has the word log written in it. Okay? And what I'm saying on this is log base A of x. Okay? A has to be a positive constant, and it's actually going to be the inverse of what we just did. So instead of going through the point 0, 1, it's going to go through the point 1, 0. And just so you know, if I have log base 10, well, I think that's going to be right here. I get something that's stretched out really far. So this would be like log base 10 of x. Whereas log base 2 of x would go through a little bit higher. 10, 1, 2, 1. There we go. Still goes to this point. So it looks very similar up till here. But it's going to grow a little bit faster if I have y equals log base 2 of x. Like I said, 1.6. I'm going to do nothing but a log review. We'll dig in a little bit deeper. Logs are going to play a big part in our year this year in calculus. So I just want you to go through. I want you to classify all of these and hit pause. And I'll write my answers up here and then hit play once you get yours and we'll see if we match. So go ahead and hit pause. Here's the answers I would have gotten on these. A couple of these I'll take something different. For example, this power one right here could be a polynomial, but a power function would be a better answer on that. And like we talked about with this algebraic function, it's a hot mess, and so just look for that hot mess label with algebraic. All right, that is all I have for you guys. Homework is here. We'll be working on this in class. If you have any questions, you can comment on the video, and we'll put those on the board whenever we get in.